My name is Gao Fei. I'm a PhD candidate at Tsinghua University. The paper I will share today is titled On Saving Outliers for Better Clustering Over Noisy Data. I will present according to the following points. The main motivation of this paper are as follows. As we know, dirty data will affect subsequent data analysis. For example, it will lead to wrong clustering. As shown in the figure, dirty values are introduced by mistakenly recording watts in inch instead of centimeter. These dirty points will form a new cluster. At the same time, the connection in the whole cluster C2 is broken, so that C2 is wrongly divided into clusters C2 and C3. For another example with car data, as shown in the table, the data will count the attributes of load, speed, transmission, torque, and so on. To ensure that most of the data are collected, and the collected data are enough for further data analysis. In addition, with the statistic, we can also find problems encountered in data collection. So we can find that the red data in the table are errors because other attributes in the table have large numbers, and the red data are obviously less than the value of other attributes. They are 0 or about 5. So it is most likely that there are errors in the data. And cars counted by these two tables may be new cars or doing some other works. We provide the data with parallel coordinates. The blue lines and purple lines can be regarded as two clusters. As shown, the trends of the red lines are different from blue or purple lines, and the value of different attributes fluctuate a lot. For instance, with the attribute speed, there is a sharp decline and a sharp rise, and with the attribute oil rate, line drops rapidly. Similarly, with attributes transmission, speed, and torque, this line also drops sharply. Consequently, these two red lines are dirty outliers. And with these two outliers, the clustering result may be changed. It may merge two clusters into one big cluster. For GPS data, we collected the time step, the longitude, and the latitude to record the trajectories. We can see that the points with time step T13 has longitude errors, and its time step and latitude are normal. And there are two points have same time step with T18. It is obviously wrong. This T18 in the red circle is more likely an error with wrong time step, and the points with times T18 is the dirty outlier. In addition, from the parallel, we can find that points with timestamps T29 and T30 are different from other data points. They might be the points in other trajectory. To sum up, error points T13 lead to a small cluster, and these error points with T18 will also form these two wrong clusters. And without these arrow points, there should be a big cluster, which means that the outliers really affect the clustering result. Another motivation is for string example with restaurant dataset. We collect restaurant names, regions, and specific address. And the record matching can make a summary list of restaurant information. Similarly, for the RD points should be adjusted into road. The ROA points and the RON points should be unified. This S should be added and the daily should be adjusted to delicatessen. The Los Angeles and Chinatown should also be unified. With these errors, the record matching will not perform well, especially for this region error. The Los Angeles and Chinatown have large distance, and similarly for Delhi and Delicatessen. Based on the above motivations, we propose method disk. Let R be a set of all these tuples shown in the figure. And epsilon is the distance constraint. R epsilon t is the epsilon neighbors of t. That is, the tuples in the blue circle. In other words, all the points in the blue circle form R epsilon t. By the way, in this example, the parameter eta is 5. That is, there should be at least 5 epsilon nearest neighbors of t. Our problem definition is that given the above parameters epsilon and eta, the outlier TO, we should find the best adjustment TO prime, such that the epsilon neighbors of TO prime is larger than eta and the adjustment distance is the smallest, as shown in the figure. The hardness analysis of the problem is as follows. Given an outlier TO, distance constraints epsilon and eta over R, and M attributes, the distance constant delta, then there is a problem of finding adjustment TO prime of TO, such that the number of points in R epsilon TO prime is equal to or greater than eta, and the distance between TO and TO prime is equal to or less than delta, and the problem is NP complete. For the main idea of our method, we give the lower bound and upper bound for optimal adjustment TO prime. The upper bound is the approximation adjustment of TO prime. The lower bound is for the determination of TO prime. In other words, the adjustment TO prime is out of the blue circle. That is the lower bound, and the range in the range of the red circle, that is the upper bound. For how to get the lower bound to be specific, we first divide attributes into two groups, the unadjusted attributes X and the other ones. When we do adjustments, the unadjusted attributes will not be changed and we only change the other attributes. With parameters eta and epsilon, let T1 be the eta's nearest neighbor of TO in the blue range, And the blue range is the R epsilon TOX, that is, with unadjusted attributes X. Points in the blue range are within the distance of epsilon to TO. Then, the distance between T1 and TO is greater than epsilon, obviously. Any feasible adjustment TO prime always has relation that the distance between TO and TO prime is equal to or greater than the distance between TO and T1 minus epsilon. In other words, the distance between TO and TO prime is always equal to or greater than this distance, and this distance is the radius of the blue circle, that is the lower bound. In other words, the adjusted TO prime is always out of the blue lower bound circle. Then we show the upper bound of TO prime. If there exists a tuple T2 in the blue range, and T2 has at least eta neighbors with this radius distance, that is, the distance of epsilon minus delta TOX and T2X with unadjusted attributes X. Then we find upper bound TOU, and TOU has same value of unadjusted attributes with TO and same other attributes with T2. Then TO must have an adjustment TO prime within the distance between TO and TO prime equal to or less than the distance between TO and TOU. That is the adjusted TO prime always in the red up bound circle. For time complexity, it is m to the power of k plus 1 and times n. There is at most k dirty attribute values in a tuple, and at least m minus k unadjusted attributes. This is because in some real cases, users can be confident on certain attributes. For instance, a wind turbine would be automatically switched off if there are more than k sensors broken. That means that there are at most k attributes with dirty values. If we don't know the dirty attributes, we can have the general complexity of 2 to the power of m and times n. For experiments, we use these real datasets. In GPS datasets, the errors are manually identified, and for other datasets, the errors are injected. The criteria are F1 score, NMI, ARI, precision, and recall. As shown in the figure, with appropriate parameters, the clustering results and disk and with DBScan have better performance. From this experiment, we can choose 3 as the distance threshold and choose 18 as the neighbor threshold. Similarly, we note that besides clustering, other applications also benefit by saving outliers. such as the record matching with restaurant datasets. Similarly, we can use 4.6 as the distance threshold and choose 2 as the neighbor threshold. And for classification in different datasets, the classification results and the disk have better performance. To sum up, our motivation is that clustering is distracted by errors, and the traditional clustering methods simply ignore the outliers such as dbScan, or assign them to the closest cluster anyway, such as in k-means. Our main idea is to save outliers for better clustering. We minimally adjust errors values of the outlier to make it appear normally, and the points will be clustered without distracting others. Our contributions are as follows. We show the NP harness of the outlier saving problem for clustering, and we propose lower bound, up bound for optimal solutions. And from the experiments, we can find that the clustering, classification, and the record matching performances are improved. Thank you for listening.